Okay, good afternoon and welcome everyone to the Oxford Martin School and to tonight's talk from Vlatko Vedral. Vlatko is the Professor of Quantum Information Science here at the Department of Physics in Oxford. He's also the Professor of Quantum Information Science at the same time at the National University of Singapore, which he assures me is a quantum thing to be able to do. He's published over 200 papers on quantum physics. He's also written 2 textbooks. He is much decorated. He's been awarded the Royal Society Wolfson Research Merit Award and the World Scientific Physics Research Medal. And we're very pleased that here at the Oxford Martin School, he is our co-director of the Oxford Martin program on bio-inspired quantum technologies. Now, his research, briefly, is looking at what quantum mechanics really actually means and how it affects everything that we see around us. So it's no small thing. But fortunately for us tonight, he's also a great popularizer. He makes multiple media appearances in broadcast and print media. He's written a popular science book, which he may try to press on us at some point during the talk. And so there's no better person to tell us tonight about living in a quantum world. Vlatko.
Thanks very much, Julian, for the very nice and concise introduction. So what I'd like to tell you about is about something that I think Jim Martin would have enjoyed very much. He kept asking these questions about consequences for our understanding of the world if the whole universe really was quantum mechanical. And I think that's what the talk is all about. I'll tell you, I'll have a very, very quick lightning review into quantum mechanics. I think it's going to be 1 slide on quantum mechanics. That's next slide. And I'm going to try to teach you all quantum physics that you really need in that slide. And then I'll progress with experimental evidence that we have for this, actually. So it's really going to be like a mini lecture on quantum mechanics. And then I will start to become more and more speculative, so you should probably start to distrust me more and more as time goes on. But I'll be very scientific about it. I'll tell you exactly where you should start to be more and more skeptical. And actually that's the interesting part as well for me, because it's fully open and for us to explore. And that's precisely what the cluster that Julian mentioned actually is doing. So here is I think this is probably the best way of introducing quantum physics, because it is an experimental way, but it's telling you about 2 key features of quantum mechanics that discriminate it from classical physics. And the title comes from 2 complaints of Einstein's. He was very, very critical of quantum physics. His first complaint was that he would say, I don't believe that God plays dice with the universe. So there is a certain random aspect that quantum mechanics says is fundamental. At the most fundamental, simplest elementary level, all quantum events are really random. And usually we illustrate this with a very simple experiment. It's you know, I'm going to use a photon here because it's very, very easy to do this experiment. But then I'll later show you all sorts of objects that we've tested this with. So we're quite confident that the world really is like this at this level. So if you send a photon and you have this mirror here, the mirror is called a beam splitter because it splits this beam into half. And you can think of it as your sunglasses. You know, there is a probability, if you like, that the photon gets transmitted here, and there is a probability that the photon gets reflected, and you can call them 50-50 if you like. You can tweak it to anything you like. The point that Einstein was making and why he was dissatisfied is that there is no deterministic way of predicting which of these detectors will click each time you run the experiment. So, you know, you get up, you have exactly the same breakfast, you make sure that all the conditions inside your lab are identical, the temperature, anything else you can think of. You press the button on your laser, a single photon comes out, and you run this experiment, and there's nothing in quantum physics that tells you which of these 2 detectors will click. You can't make that prediction. It's random. There's no description. There's no hidden description. I don't know how strongly to put it, but I think one way is to use Einstein's language and to say even God doesn't know which way the photon will go. Okay, bless you. Of course, I'm using God in a very metaphorical way. I'm a physicist, as you understand. It's the same God as appears in the title here. So Einstein couldn't accept that this is genuine and random. There's no description. It's very ironic, incidentally, that this is one of the most profitable applications of quantum physics. This is how you generate random numbers, and they use this in the casinos of Las Vegas. So, you know, God doesn't play dice, but we definitely do, and it's the best way we have of ensuring absolute randomness. There's no pseudo-random number generator behind this. Now, what was the second complaint? The second complaint is that it also allows for spooky action at a distance. And here is an interesting extension of this experiment. So it's the same beam splitter here. And then instead of detecting the photon, you see, Einstein would have objected to this immediately as well. He would have said, what difference does it make if you decide to detect something or you don't detect it? The world is out there. It's real. And it shouldn't make any difference whether we decide to engage with it or not. How can that change the rest of the world? And actually it does, according to quantum mechanics. So if you don't detect the photon, but you put two reflecting mirrors and you recombine these two possibilities, what you do now is you insert another beam splitter. And here is how a classical physicist like Einstein would have argued what you should expect. So the question is now, I fire a photon, it goes through the first beam splitter, then it goes through the second one. Which of the two detectors should be clicking now? And I've spent about 5 minutes convincing you that this is the most random thing you can imagine in this universe. And all I'm doing now is putting another random thing afterwards. So it's got to be random. I mean, you know, you can do another kind of analysis. You can say the photon comes to the beam splitter, tosses a coin. If it's heads, it goes one way. If it's tails, it goes the other way. Comes to another beam splitter, tosses another coin. If it's heads, it goes one way, tails goes the other way. So if I did this experiment, I should expect half of the photons on average to go this way and half this way. Okay, and that's the interesting statement about it. And actually, quantum mechanics contradicts this 100%. This is never what happens in the lab. What happens instead is that every time you fire a photon here, it always comes out in detector 1. It never triggers detector 2. How can that be? You know, this is very weird, because this is a little bit like me offering you to bet on me tossing a coin, to which you should surely reply, I'm not going to bet on that. It's a random event. I'll be losing money if I bet on it. Then I pull out another coin and I say, look, now I'm going to be tossing 2 coins. Do you want to bet now? And if tossing coins was quantum mechanics, then you should say, yeah, I'm definitely going to bet now. I know exactly the outcome. Okay? So this is what quantum mechanics says. You put 2 random things together and you get a 100% deterministic outcome. How can that be? And this brings us to the spooky action. The only way we can understand this, it really is the only way. Whatever interpretation of quantum mechanics you like or you read about, they all have to say the same thing about this experiment, really. There's no difference there. What you have to acknowledge is that the photon really goes both ways at the same time. So you're now thinking of a photon as a wave rather than as a particle. And then these 2 waves, when they come to the second beam splitter, they really cancel each other out when they go in this direction, just like water waves. One has a maximum and the other one has a minimum, so on average it's 0. And they actually tend to constructively amplify one another, and they go this way. Okay, so somewhere there in the game, you have to acknowledge that the photon really exists in both of these arms of the interferometer. Why is that spooky action at a distance? Because here is how Einstein would have argued. I can have a telescope here, and I can be collecting photons coming from a star behind the sun. And because sun can attract these photons gravitationally, we know that. That's one of the conformations of general relativity. What quantum mechanics would say is that every photon coming from that star takes both routes around the sun to come into my telescope. So this is a huge interferometer now. There's a photon coming from a distant star, and simultaneously it takes the right-hand part, if you like, and the left-hand part around the sun. So it's a huge superposition. And what Einstein would have said is if you decide to check which way the photon goes, and you stick in a detector in one arm, if you don't get a click there, that means there is no photon here, and what that means is that you've created a photon in the other arm of the interferometer. And quantum mechanics says you've done that instantaneously. You don't get a click here. At the other side of the universe, there is a photon that immediately appears, and you have to get a click in the other arm. And it sounds as though you should be able to communicate faster than the speed of light with this. That's why Einstein didn't like it. He said spooky action, you know, it seems to contradict relativity. And of course, he liked relativity very much himself. So basically, I'll tell you a little bit more because I really decided to be completely honest with you, even to the point of maybe boring you with all of these details. But basically, why doesn't this work? And it's a very intriguing answer. So you can say, imagine Alice and Bob wanting to communicate, and Alice is sitting here close to one of these parts and Bob close to the other one. Okay, so they could be on two different planets, if you like. And Alice asks Bob, you know, would you like to go on a date with me tonight? And she wants a clear answer, yes or no, to this question. And so what Bob does is sticks in a detector here. And if he gets a click, that means Alice won't get a click. That's a no to her question. And if he doesn't get a click, that means Alice will get a click, and that's a yes to her question. And here is the spooky action. They can instantaneously communicate this one bit of information. And you know what saves the game? What saves the game is the fact that God plays dice. Bob cannot decide whether he gets a click or he doesn't get a click. The bottom line is that it's a completely random event. So even though Bob really would like to send yes or no, he doesn't decide which of the two messages get sent. And all Alice gets on average is a random answer. But she doesn't want a random answer. That really means nothing. She wants a clear yes or no. So there is a nice way of putting this, that God plays dice with the universe in order to save relativity from the spooky action at a distance. Okay? And this is all there is to quantum mechanics. You can actually elevate the two complaints of Einstein's to axioms, and you can derive quantum mechanics from more or less these two assumptions. I think that testifies to the stature of this guy as a scientist. You can take his complaints and derive a new theory just from his complaints, okay? Imagine what he was like when he wasn't complaining about stuff, okay? Well, we call that general relativity, of course. So the bottom line is, if you ask yourself which part is taken, you have to say both of them are taken, and that's your famous superposition there. So it really takes both of these routes. And here is something that we'd like to do, actually. What we'd like to do, I'm just showing you because this is of direct relevance to what the Martin School is funding. What we would like to do is actually excite a molecule inside a very small confining cavity. And then we'd like to get that molecule to emit a single photon, and then we are basically testing the randomness of that photon, because when you put a beam splitter here, you can really see whether the photon goes one way or the other. But then you can do even something that's more fun, because you can show that the quantumness that comes out of the laser goes into the molecule, comes out into the photon, could go into another molecule, and come out and behave the same way. So actually what this experiment would somehow demonstrate is that the weirdness of quantum mechanics that I'm talking about is not just at the level of light, of photons, but you can make any material object exist in many different states at the same time. And it would all be a kind of slightly more complicated variant of an experiment of this type. And I'll show you that as we go along. So how far have we tested this? This gave, of course, numerous debates between the pioneers of quantum mechanics, and this is one of them that I already alluded to. So I think here Einstein was saying, I can't believe it's like that, I'm a realist, and the world should really exist objectively out there without us having to interact in any specific way. The other position, almost diametrically opposing, was taken by Niels Bohr, He was someone who you would call a pragmatist, an instrumentalist, or something like that, where he would say, oh, you know, we shouldn't worry about quantum world. There is no quantum world. All we are happy with is that there is a physical description. So basically what we need to know is that we can predict the outcomes of our experiments. It's all about what we can say about nature at the end of the day, rather than what really happens between the laser and the clicks in the detector. So he was happy that quantum mechanics gives the right statistics to detection, never mind what happens in between. Is it really in two places at the same time and all of that? This was in the house of Paul Ehrenfest, and I had the privilege of being one of the few. It's a private house. I think the Dutch government is desperate to buy that house of the individual that I visited, and he's not selling it. I wouldn't sell this ever. Because on the wall of one of his rooms upstairs, this is where all these debates took place. And when you read the signatures on that wall, it's literally who's who in the foundations of quantum mechanics. Anyone who's done anything in quantum mechanics has actually been a visitor of Paul Ehrenfest. It's an amazing piece of culture, actually, and I hope it's still preserved. Now, fortunately, in some sense, because this is really all about philosophy, I don't want to complain too much about philosophy. I know some of you are philosophers here, so I'll try to be nice tonight. Both of these arguments were destroyed by another physicist. Basically, you can't really take this position, and I don't think you can really take this position either. And the person was Schrödinger, of course. So Schrödinger somehow said, although originally we talk about classical physics applying, basically being applied to large objects that are very slow, if you like, and thinking of quantum physics as traditionally describing subatomic, atomic objects, and so on. Schrödinger would say that's not the key difference between the two, because of course there is a domain in between, and the question is what happens in between. And Schrödinger would say you should really think of the phenomenon called entanglement, and I think everyone knows about it, as the main difference. And he wrote this paper. He wrote two papers, actually. He was bilingual. He wrote two papers, one in English and one in German, where he introduced the concept of entanglement. And I think his main point there is that if small objects can exist in two different states at the same time, and small objects couple to large objects like us, I mean, after all, we're just a bunch of small objects, like atoms coupled through light, then actually it must mean that this quantumness of small objects can somehow infect a larger object as well. And where do you draw the boundary? You know, why should quantum mechanics stop at the level of small objects? So you can't be a realist once you realize that the whole universe is entangled. And I think this is the question I mentioned Jim Martin was very fond of asking all the time. What does it mean for the universe to be in an entangled state? And you also cannot hide behind being a pragmatist, because once a large object is confirmed to be in a quantum state, what does that mean, you know? You can't say it's a weird small world and it doesn't really apply to large objects. If it does, then you have to rethink what this really means. And that was the point Schrödinger made a long time ago. So here is, I love showing this. Here's what my students do. Here's the Schrödinger cat. So Schrödinger, of course, the large object in his example was a cat that was either dead. This is a snow cat from Les Ouches in France, where they do schools of physics every year, and it's a great opportunity for our students not to attend lectures at the school, but to do stuff like this, I think. Here is the alive cat. So basically, his point was very simple, that if you think about this, I think I even have a picture of that maybe. If you think about this interferometer, where the photon takes two different routes, then he imagined that in one of these arms you put a bottle with poison, and the photon, let's say, breaks the bottle, the poison is released, and the cat that's sitting in the same room dies as a consequence. But quantum mechanics says equally likely the photon will go the other way simultaneously, in which case there is no bottle with poison and the cat stays alive. And suddenly I've got a microscopic event which takes place and doesn't take place simultaneously, affecting a large macroscopic object which can then be dead and alive at the same time. So what does that mean? I think he meant it as a paradox, but then he slowly changed his mind. You know, he became what we call a many worlds personality. He actually thought there's nothing wrong with this. You know, why not? And that's the attitude that experimental physicists have, actually. That's great, you know. Why not? Why not? Let's try to do it, you know. And it doesn't stop there. So this is, again, something that Jim Martin would definitely ask, because what if there is a person doing experiment outside of the whole experiment? They look at the screen, and they see a dead cat in one case, and they see a live cat. What does that mean for them? It would just mean that they're equally happy and sad. You know, there's one universe in which they're happy because the cat is alive, and there's another universe in which they're sad because the cat is dead, and so on. So that's basically, and it never stops. The whole universe would now split in exactly the same quantum mechanical way. This is the logical conclusion of quantum mechanics. Of course, we don't know if the world works like this. That's the exciting thing. So people have gone on to do all sorts of experiments to test what kind of objects can be in many different states at the same time. This was a breakthrough experiment, a famous one, almost 20 years old now. So this is a group in Vienna that said, why don't we take a very large molecule? I'm saying this as an atomic physicist. Basically, this is very large in the sense that it contains 60 carbon atoms. And what this slide says is that this is a prediction of how small the quantum mechanical wavelength of that object would be compared to the size of the object. So the size of the object, its classicality, if you like, is 1,000 times bigger than its quantumness. So when before the group in Vienna did this experiment, they had 6 theoretical physicists trying to predict the outcome of this, and all of them got it wrong. None of them predicted superpositions. All of them had different arguments why you would never see a quantum mechanical feature in a molecule like this. I wasn't one of the 6 physicists, but I'm sure I would have made exactly the same mistake there. So, you know, first-year undergraduate textbook tells you that if this is really so much bigger than this, it's classical for all practical purposes. They went ahead, fortunately, to do the experiment, despite all the predictions. And here are the molecules coming out at 1,000 degrees Kelvin. And I emphasize that because it's a very high temperature. And that means they even emit lots of radiation on their way. So you collimate them here, make sure that they go in a straight line. Here is a diffraction grating. And what you're asking is, every time I fire a molecule, does it go through one of the slits at a time, or can it really superpose itself and go through many slits simultaneously? That's really the same key feature that we talked about before. And here is this is the picture without the grating. They just wanted to show that the molecules really go in a straight line. And this is a picture with the grating. And this is a picture that's indistinguishable from what you would get from photons, or what you would get from water waves, or anything else that actually interferes as a wave. So even though this looks like a large molecule, it should be classical. In fact, according to this experiment, it's also fully quantum mechanical. So each molecule, this is one molecule at a time, tends to go through simultaneously through many of these slits. And that's the only way to get this kind of pattern. And that's really nice. I just want to show you this experiment with another atom, just because I have the real data for this experiment. So what you do is, here is the screen at which you detect the atoms. And these faint green dots, each of them represents a single atom hitting the plate. And here is, if you wait for about 5 minutes, you can see that this is micron, so this is hugely amplified, of course, for us to see. This is the pattern you get after 5 minutes, and it looks pretty random. You can't really tell whether this is quantum or classical. Then you wait for about an hour, still doesn't look that clear, actually. Almost 2 hours, and beyond that, you're starting to get fringes, as we call them. You're starting to get lines where quite a lot of molecules tend to fall onto, and you're starting to get areas where none of these molecules fall onto. So if you wait, 8 hours, 16 hours, it's a long experiment. you have to keep your PhD student locked up in a basement room, I think, to wait for it. It's 2 days, okay? You only give them food after the experiment is done, I think. So you can see these dark fringes where there's a high chance of these atoms hitting the screen. And then you can see lighter ones where they're unlikely to do. And again, if you look at this picture and someone shows you the picture, you won't be able to tell that this is an atom and not a photon or not whatever else interferes. And here is an even bigger object that they did, and they basically interfered that and so on. So the question is, of course, how far can we go? This is probably the most exciting question, certainly in physics, even in the whole of science, maybe. I mean, I'm slightly biased being a physicist, but I think it's a really fantastic question. Does it hold at every scale? We don't know. So, you know, we've done it with small objects along the way, with neutrons, atoms. What about protein, you know? That would be nice, an even bigger molecule. Some people are proposing doing this with a virus. Because believe it or not, there are some philosophers out there who believe that something weird will happen with quantum mechanics when it encounters living systems like us. I think we're relatively close to superposing a virus in 2 different places, and I'm really curious to see what the response from these philosophers will be, okay? They will have to shut up and think about something else, I suppose. So even a virus will interfere. Why not? I mean, what's there to stop it? Now, there are some smart people who have answers to this question, actually, and that's why it's an exciting issue. There are people who claim that somewhere along these lines, somewhere there, something will happen that will collapse quantum mechanics. There's a famous GRW model, which simply says, look, it's obvious that large objects are not in 2 places at the same time. So we've got to modify quantum mechanics. We don't quite know where, but somewhere along the way it will collapse. There's a slightly better motivation, which is that gravity might be the thing that makes larger objects classical. And there are all sorts of exciting questions related to this one. And we are getting closer and closer to being able to test that. There are many ways of arguing this. You can say that quantum mechanics says that gravity, that space and time will fluctuate at very small dimensions. So if the particle takes one spatial direction, or it takes the other one, there will be some uncertainty into exactly what path the particle takes. And these uncertainties will add up in a way to collapse quantum superpositions and make the whole thing classical if it's a large object. And you can make all sorts of predictions based on that. And this really is a very exciting direction because we don't know what's going to happen. So this is a joke slide, obviously. This is not what we are planning to do. And this is not how you would, of course, test Schrödinger's cat. You wouldn't really fire a cat at 2 slits and see whether the cats diffract. You would do something else, actually, and that's what I want to tell you about. I want to tell you about the difficulty of these experiments. Every time I look at this, I really cringe because I love cats. I'd be doing this with dogs really happily, but I don't know why. Schrödinger made a mistake there, I think. So now, what you need to do, I just want to demonstrate to you why this is a difficult experiment. You know, why don't we do Schrödinger's cat? And you know, is it really dead and alive or dead or alive, and what's going on there? And the tricky bit is exactly what you would have to do to confirm that experiment is what you would have to do to confirm any quantum experiment. You'd have to recombine the 2 possibilities that are simultaneously superposed. So half of the experiment would be to make the cat dead and alive. That would be only half of the experiment. And if you come in and say, how do you demonstrate to me that you really have a dead and alive cat? What you typically do is try to recombine these 2. That's called an interferometer, exactly like the one we saw. So in some sense, it implies being able to reverse the 2 possibilities and see whether you get back to the initial state or not. Okay? And as soon as you hear reversing the 2 possibilities, you know that one of them is being a dead cat. So what does that mean to reverse a dead cat and bring it back to living? Of course, it's a very tricky question. You know, it's tricky doing that with a complex physical system, let alone with something that has biological features. So this is an operation that a friend of mine calls the Lazarus Operator, you know, bringing the cat back from the dead. And that's more or less what you would have to do to confirm this experiment. I wrote, maybe somewhat provocatively, that it's just a question of money. If you give me enough money, I'll probably be able to superpose anything you like. But we don't know that. Maybe something interferes in the way. So it's literally like putting this cat in the interferometer, making the superposition, and then recombining these two and asking, does it only get a click in detector 1, or would I sometimes get a detector 2 to click? If you've eliminated all other sources of noise when you do this experiment, and that's a big if, and if you get detector 2 to click, it's the end of quantum mechanics. That's a definite Nobel Prize in physics, definite. It's probably not going to happen. I'm not betting on that. And that's kind of boring that it's so successful, the theory, but I think it probably will hold it at some larger level as well. So here is our equivalent. Like I said, we are not, we're not going to use any cats or dogs or anything like that. It's very complicated for us physicists. We can't even understand a molecule properly, let alone a living system. So what we'd like to do is take a laser, split the photon, and then in one arm put one of these molecules, organic molecules that I was telling you about. And you can take your pick. We're using currently a very simple organic molecule because we know how to excite it properly and deterministically. But you can put more and more complicated molecules here. And what this experiment does is if the photon goes this way, it excites this molecule. But if it goes this way, it excites this molecule. And since quantum mechanics is telling us that it goes both ways, that means both of them will be excited and de-excited at the same time. I'm going to use Schrodinger's language. This guy will be dead and this guy will be alive, plus at the same time, vice versa, this guy will be dead and this guy will be alive, excited and de-excited. This is your Schrodinger's cat with an organic molecule. You can stick in a virus here and test the same thing if you like. It's hard to control that, of course. And then you collect these two and you look which way the photons come out. So this is something from our lab. And these are the experiments that we would like to develop with Robert Taylor. I think Dave Coles, who is here in the audience, is also working on some related experiments like this. So this is what, so you know, I'm originally a theoretician, but as a consequence of my midlife crisis, I'm becoming an experimentalist, okay? That's what we theoreticians do when we hit midlife crisis, you know, let's go into experiments. And then you can scale it up. You can say, oh, I can have lots of these cavities. I can have an array of 20 by 20 cavities. And if I make sure I spread my photon equally across this area, maybe I can entangle 400 molecules at the same time. And that would be fantastic for our technology as well, because you'd be going towards quantum computers with something like organic molecules as qubits. And the question is always the same. You know, can we make a large-scale quantum computer is identical to the question of does quantum mechanics really hold at this level? It's one and the same. There's no difference between technology and foundations as far as physics is concerned. So I want to tell you towards the end, I don't know how much time I have, but maybe 10, 15 minutes, I think. It's okay? 10 minutes, 10, 15 minutes. I want to tell you about another possibility. People are writing popular books about it, so I might as well tell you about it. The question is maybe some macroscopic quantum effects are already out there. Maybe we don't have to work hard at creating it because nature had 4 billion years to evolve it anyway. So why not rely on natural selection to maybe utilize quantum? If it's so good and so beneficial for computation, then maybe it's out there already. And this is a field that's called quantum biology. And actually, there is a physical foundation for that. So a few years ago, there was an experiment which took quite a large, a few milligrams of a piece of salt. I suppose this is a kind of a salt, and they tested the response of atoms inside this salt to the external magnetic field, and then they plotted the results, which they tried to simulate using classical physics, and then using quantum mechanics. and then using fully quantum mechanical description with entangled states of these atoms. And what they found excitingly is that you really have to use the full entangled states. These are macroscopic entangled states in order to fully comply with the experimental data. So there's no way of explaining this unless you acknowledge that even 10 to the power of 23 atoms inside this system are actually simultaneously entangled. So this is really like Schrodinger's cat. Is just an inanimate physical system. So, once you see something like this, the question is, do you really doubt that if we start to go beyond this scale, something weird will happen? What exactly is going to happen? That really is interesting there. And then, of course, once you see this in physics, so this is a typical arrogant physicist telling you about relationship between different sciences. So we tend to think of physics as the most fundamental science and underpinning everything else. And chemistry is just basically a consequence of quantum physics. All of chemistry really is just a consequence of quantum physics. And then you can say biology is just applications of the laws of chemistry. So ultimately, all of this is reduced down to quantum physics at some level, okay? It's a big if again, obviously. But if I found entanglement in big systems here, then why can't I find it in chemistry, and why can't I find it in biology? What's going to prevent me from going in this direction? Now, I have to be a little bit careful because we physicists tend to think about these things like this guy here, Rutherford, and this is one of my favorite statements of all times. It's brilliant. It's still very true. If you look at the laws of evolution, they're not the same laws as Newton's laws of motion. You can't predict anything with them. They don't have the same explanatory power. I'm not arguing against evolution. I think it's beyond any doubt. But maybe you'll be able to reduce it to something that makes more sense, something more microscopic. They're very macroscopic, fluffy statements, more like philosophical as far as a physicist is concerned. So in a way, you either have taxonomy, or you really have the hard science, which is physics. And it's still true. Whether you'll be able to reduce science to physics, and I don't know. But Rutherford thought you could be. Ironically, incidentally, he is a Nobel laureate in chemistry. He kept a Nobel Prize in his toilet. He was hiding it from people. He was very ashamed of that. He discovered the structure of atoms. And that's, of course, neither here nor there. It's chemistry or physics. For every physicist like Rutherford, there's another Nobel laureate physicist who actually claims the opposite. So Anderson wrote a very influential paper in the journal Science, 1972. No equations there, 2-page long. Anyone can read this. I highly encourage you. And he claimed the opposite. He said there are complex systems whose behavior you will never be able to reduce, even in principle, to the underlying laws of quantum mechanics, microscopic. I would be very disappointed if the world is like that. But, what does the world care about whether I'm disappointed or not? But, that's one of those. And, of course, Schrodinger again comes in. And he says, I actually, so this is a statement from his book, What is Life? And I think it's not an accident that person who thought very deeply about entanglement and what it all means also thought about scaling this up and asking, what about chemistry? What about biology? So he wrote the book, What is Life? Which was read by many physicists and convinced them to go into biology. Basically, he was saying something like this: biology is far too important to be left to biologists, okay? Physicists just go in, and this is true even now. All the major breakthroughs in biology, the DNA structure, were actually made using techniques from physics. And this is actually what we are hoping as well, to basically design some kind of novel quantum spectroscopy that will help even biologists and chemists understand complex structures of molecules and their dynamics. That would be great if we could teach them something as well. He kind of made this speculation where he said maybe the laws of biology will actually rely on some other laws of physics, not classical physics. So people always interpret this as meaning quantum physics might actually really be relevant to explaining life. Maybe you couldn't even have life without the universe being quantum mechanical. But it's a mysterious statement. Maybe he was even more radical. Maybe he was saying we should even go beyond quantum mechanics. I don't know. You know, this was 20 years after the discovery of quantum mechanics, so I'm not sure what exactly he meant by this statement. But he certainly thought physics should be applied to biology. And the two examples I will present you, and then I will stop basically. This is now, I said I was going to tell you when we are becoming speculative, and this is as speculative as it gets. All the evidence we have for biological coherence and superpositions and entanglement is at best circumstantial. That's what a physicist would say. So if you ask me this, if I'm sitting on the jury, I would say this is not beyond reasonable doubt. I mean, you know, just let him go. You know, it's not quantum, really. So the evidence is in photosynthesis, which is probably the best evidence we have. And what they tested is they took a part of the photosynthesis. So basically, the whole photosynthesis is extremely inefficient. When you add up all the parts, starting with the capture of light, transfer of light to the reaction center, and then processing chemically of this energy, people say it's between 1% and 5% efficient. So actually, you know, hopefully we humans should be able to do better than 5% efficiency. But there is one aspect of photosynthesis which takes you from the captured photon into the reaction center, which people claim is almost 100% efficient. So the photon gets captured by one molecule, then it goes down a cascade of molecules and ends up in the reaction center here. And that's reported to have almost unit efficiency. It almost violates the second law of thermodynamics, how efficient it is. And biologists couldn't explain it because biologists usually think in terms of classical physics. And it took a few quantum physicists, actually quantum chemists from Berkeley, to say, well, maybe we need to apply a full quantum treatment. And people are now debating how strong the evidence is for the fact that when the energy cascades down this way, the energy really takes all of these routes simultaneously. As far as we know, that's the only way of explaining how energy gets from here to here with 100% efficiency. So these people, they're not studying plants, they're studying purple bacteria, which usually live 1,000 meters below the sea level, where you get on average something like between 3 and 5 photons per day. So unless they are very good at capturing these photons, I don't think they would have enough energy to survive, actually, on just 3 to 5 photons. And so, you know, one possible motivation, biologically speaking, for this kind of efficiency is simply these extreme conditions in which bacteria lives. The other cute example is magnetoreception. And actually, I don't want to tell you the whole long story about this. We have evidence that you can measure the direction of magnetic fields and influence chemistry in the lab. Actually, that's what our chemists at Oxford, some of them are doing here. They can actually change the external magnetic field, and depending on that, they can get one kind of chemical output or another one depending on the direction of the magnetic field. So we know that we can use chemistry as a compass. What was weird about this proposal here is that it puts it one level up and says even biological systems, living systems like this bird, will actually use that chemical mechanism in order to tell the direction of the magnetic field. So this is the famous European robin flying from Northern Europe to Africa and then back again. I think there is a group in Frankfurt where they capture European robin somewhere along this flight, basically, and put the robin in an external magnetic field, and then they look which direction the robin moves in, and so on. And what they found in '71, what they found very weird, is that when they put magnetic field in one direction, the robin would go in this way. But when they change the north and the south, when they exchange the polarity of the field, the robin would still go in exactly the same way. And this killed the idea that this is a simple classical compass. So we know that lots of animals use a compass. You know, you have some kind of magnetic substance, and when the Earth field changes, basically the magnetic substance just follows. And that would be a classical explanation of that. But actually, they don't do that. This experiment kills the idea that it's a simple compass. And then what they discovered is when you change the angle of the field, then the robin goes the other way. But if you change the polarity again, from north to south, it's just not going to notice that. Some people think this is a great evolutionary mechanism because every once in a while, the Earth's magnetic field does swap north and south, and it would be really unlucky for them to be even sensitive to that kind of swap. So it's good to have this insensitivity. The question, of course, is how do they do it? And there was a proposal that they really use entanglement between two electrons inside a molecule that's sitting in the retina of one of the two eyes of the European robin. They know it's not in the other eye because they can cover the other eye and the robin can still go in the right direction. But if they cover this first eye, then the robin gets very confused. And to cut the long story short, we wrote about this in Physical Review Letters. This was the only paper that was ever reported in the Daily Mail that I've written. It's really interesting. So this is in the Daily Mail as well, okay? And what we found unusual is that when we looked at how long these electrons stayed entangled, and this is again, if the model is right, if all the evidence is right and all of that, there are many big ifs. But if all of this is right, then basically they stay entangled for about 100 microseconds, which at the time when we discovered was much longer than anything we could artificially do with electrons in our own physics labs. And that really surprised us that nature, with large objects at high temperature, could actually do better quantum mechanically than what we can do with our technology. And that's what attracted us to comment on that. So, you know, that acts also as an inspiration. Maybe we should be able to reverse engineer that and so on. Okay, the last thing I want to tell you about is actually, I'm going to go straight to the last slide. And I'm again going to go back to the fundamental question of what does this all mean? Again, something that Jim would have definitely liked. And the question is this. If quantum objects can really exist in many different states at the same time, and the whole universe is split into many different possibilities at the same time, how come we see any classical deterministic world emerging out of all of that? You know, why does this table look very real to me if every atom inside the table and every photon inside the table is fluffy and cloudy in the same uncertain quantum way? How do we understand the macroscopic world? And I want to give you this last slide because it's a metaphor. So now you should not take this seriously at all. And it's a metaphor I borrowed from the late American physicist John Wheeler, who thought a lot about this interplay between physics and information. And the way he would put it is like this. Imagine that you have a game which a number of people can play, and actually I learned it by playing this game as well. Imagine that you have people around the table and every person gets 4 cards. And the whole point of the game is to follow a couple of basic rules that I will tell you about. And the person who wins is the first person to end up with 4 cards of the same kind. And then they announce that and they are the winner. And there are only 2 rules to this game. So basically you start with one person, and that person can ask anyone at the table if they have a certain card. So basically I can turn to the person next to me and I can say, do you have an ace of spades? And this rule says that you can only ask for a card if you have already at least one of the cards of the same kind. So the fact that I'm asking someone for an ace also reveals a little bit of information about me. So this is this property of quantum experiments, that you can never be a passive participant. You always have to give up a little bit of your own information when you engage with nature. So that's rule number 1. I can only ask you if I already have a card of that type. And that tells others, signals to others, a little bit of information about my 4 cards. The second rule is just rule of honesty, that if I ask you whether you have a card of certain type, and if you have it, then you must give it up to me. And that's how I can end up collecting 4 cards of the same type, if you like. And you make 1 or 2 rounds, and there will always relatively quickly actually emerge a person with 4 cards of the same type. It's a very simple, it's a brainless game, actually. It's a very boring game, in fact. The only reason why this is not an entirely boring game, and I always found this amazing, is that actually you don't need any cards to play the game. There are no cards in this game. So what does that mean? That means I can sit down and imagine in my head that I have 4 cards of any kind that I like. I have a pink elephant, 1 card, a fluffy cloud, another card, and whatever else. So I deliberately come up out of infinitely many possibilities, just like quantum mechanics. I come up with 4 of them. And every participant can do the same. And I can even change my mind so long as I'm consistent with these rules. So you can ask me, do you have a pink elephant? And at that point, I'm going to change my mind because I don't want to give it up, really. And since I don't have the cards, I can change my mind so long as I'm consistent with all the questions that have been asked before. And I haven't already lied about it before. And what's amazing is that even though no one around this table has any cards whatsoever, after 1 round or so, you will always end up with 1 person with 4 cards of the same kind. And that's really amazing. And I think it's the closest I can get to how something deterministic and classical in a way can emerge out of something that's completely open and uncertain to start with. I think that's the kind of best metaphor that we have for the quantum to classical transition. Thank you for your attention. I'm happy to answer as many questions as possible, and I think Julian mentioned that I should be my own chairperson and I can coordinate the questions, but if you have a question, please wait for the microphone, just because everything is recorded and it's live online. So be careful how you phrase your question as well. I think many people are watching this program. Yeah. Thank you.
I read something, I don't know whether it was the experiment that you were talking about. It was about splitting, I think, an electron, and then it went into 2 things which resonated, so it had phonons in there, and then these somehow... And what confused me was how, I mean, if you have an electron or a photon, then your quanta is very clear, but in a phonon, what's going on?
Yeah, I think it's a really important point, and it's good to emphasize this again. So, quantum mechanics might be weird, but it's consistently weird for every possible object in this universe as far as we are concerned. So any particle, and you can think of particles as simply excitations of whatever underlying field is there. In your example, a phonon would just be 1 quantum of vibrations of whatever object you're looking at, a molecule or a crystal or whatever else. And what you can do is exactly what I presented with molecules. You can split a photon and make sure that you excite 1 unit of vibrations in one of these molecules, and at the same time you excite 1 unit of vibration in the other molecule. So you can think about this as a kind of macroscopic entanglement, but now between vibrational degrees of freedom of this system. And it works exactly the same way. So quantum mechanics is kind of fully consistent, and there is a beauty in this picture because you can think of every aspect of matter or light as a quantum bit, if you like, in exactly the same way. I'm not sure I answered your question because you might have had a...
The fact that you can't have half an electron, but
That's right.
You could have half a phonon.
Well, you don't have half a phonon. That's what's unusual. I think when people started discussing superpositions, there were suggestions that you have a half photon going one way and half the other. In fact, Heisenberg, out of all people, made this suggestion. He made all sorts of interesting suggestions that energy conservation is violated quantum mechanically as well. He was very adventurous. I mean, he was wrong, but when he was right, he was really right, okay? But the way we would phrase this is that if you really detect that phonon, if you put a detector to see whether there is a vibration or not, you will either get a click saying, yes, there is one phonon, or you will not get a click, which means that the phonon exists in the other location. But you will never get half a click. We never detect half a particle. So it's really one single quantum in the same way that other objects are particles as well.
Thank you. I was wondering if the superposition of viruses is going to be tested. In which way is this going to be done?
Yeah, very good point. I think what they're trying to do is, so I think as with lots of these experiments, physicists would do it by trying to eliminate all sorts of noise. So frequently, that, for us in atomic physics, that means cooling objects down to very low temperatures. So if we want to do this with billion atoms, if we want to put billion atoms in two different locations at the same time, and we've done that, then you would have to cool them down to a billionth of kelvins, you know, billion times lower than the temperature around us. And that's very hard to do, and it's very costly. Now, if you do that with a virus, you could say, is that still a living system? You know, is it, first of all, biologists doubt that this is really living, and for all sorts of other reasons. So probably you should up it to bacteria or something slightly higher. But I think the way you would do it first as a physicist is you would probably capture it within something that's much easier to put into a superposition. So I think one proposal I'm aware of is to take a metallic sphere and then put a virus inside and induce some kind of vibration inside this sphere. And this is something that you would call a nano because it's very small, nanomechanical oscillator. And this is the direction that people are taking. So you want to cool it down to sufficiently low temperatures that you can claim that when you make oscillations of this sphere, the sphere really exists in two different locations at the same time. And therefore, whatever is within the sphere would also be in a superposition of these two locations. So that's one experiment that you could do. But then you can ask, of course, what if you up the temperature and, you know, if you want to have a genuinely living system that's still alive when it's in a superposition, then it becomes much harder.
In quantum physics, when you do an experiment, you influence it, and that kind of goes against that whole beauty of science being objective. So how do you feel about it?
I'm not sure if it's a question of objectivity, you know, because there is a really interesting consistency in this whole picture. You might say it's subjective in the sense that I decide to engage or I don't decide to engage. But actually, consequently, whoever else decides to engage within the same experiment will have to observe exactly the same outcomes that are consistent with the outcomes that I've observed. So that's really weird. That's kind of unusual if you think about it. So, you know, I enter the room with dead and alive cat, and I see an alive cat. And then you say, I'm going to come in after you. I mean, why shouldn't I be able statistically to see the exact opposite outcome to what you see? And actually, quantum mechanics says this is impossible. You're always going to see exactly the same outcome as me. So in a sense, there is a certain objectivity to this. It doesn't kill determinism either, because you know, the fact that I made a free choice and it feels to me free might well not be free as far as the underlying quantum mechanics is concerned. Maybe I think I'm free because I'm so entangled to the rest and I'm not thinking about these entanglements that I appear to myself as a free agent. But actually, quantum mechanics has nothing to say really about free will, you know? It's neither here nor there. And it's consistent. Yeah. Sorry, I'm cutting corners whenever I answer questions, so please ask me more if this is not what you wanted to hear, actually. Yeah.
Hi, I was wondering actually if you could just elaborate a bit on what you just spoke about. And my question, I suppose, would be just in terms of how you look at the world or how you look at life.
Yeah.
Does spending so much time thinking about the quantum realm change the philosophy or the outlook that you have to sort of the macro existence that you have?
I think what's interesting about that in my case is really that you have consistency between two almost opposing views. You know, the Copenhagen and the many worlds, if you like. So a Copenhagen person would say, for you to even meaningfully talk about experiments, this is what Niels Bohr would have said, for you to even meaningfully talk about experiments, you need to have the classical world somewhere outside. So you and I might decide to do an experiment that might be genuinely quantum mechanical, but when you and I are explaining that to one another and doing calculations, that's actually now the classical world. And that's fine so far as the experiment, you will get the right predictions. But equally, and Heisenberg made this point really forcefully. Heisenberg was great, actually. I think all of us physicists really feel like Heisenberg did, you know, in terms of interpretations. So Heisenberg would say, that's fine, but you can actually put that boundary wherever you like, and it's still going to be consistent. So Heisenberg would say, let's now calculate what would happen if you quantize two of us and do exactly the same experiment. And you would get exactly the same predictions. And then you say, what happens if I quantize the Oxford Martin School and look at the same experiment? You get exactly the same prediction. So one school, so I think ultimately it boils down to the following question. Is there really, beyond some limit, a genuine classical world? Or is it just classical for all practical purposes, meaning I don't need to quantize beyond certain scales in order to explain microscopic experiments here? And it's interesting that these two, they sound like very different views of the world, but they still haven't clashed at any experimental level. And I said we physicists are like Heisenberg because this is what philosophers usually tell us, you know. I have a good friend of mine here, Harvey Brown, and whenever we talk, he says, you physicists, you are so opportunistic. And he means it as a criticism, actually, something bad. But you know, we are opportunistic. I mean, we're facing something much smarter and more powerful than us, you know, the rest of the universe. And I think you've got to use all your abilities, all the opportunistic possibilities in order to understand it. And I think having the multitude of views about what's really going on is really helpful because different circumstances might be more suitable for different ways of looking at that. But let me tell you the punchline. If I really genuinely show to you that as you enlarge this universe, the quantumness in the universe, if I really show you that the rest of the universe is quantum, so for example, I show you that there is entanglement between me and a distant object, then I think it would be very hard to maintain the Copenhagen view. It really would be very hard to do that. And that can be tested, at least in principle. So if I show to you that it really applies to large objects, then I think it's very hard to maintain some of these interpretations. That's what I would say. Yeah. There was one more here. I don't know if...
Yes, so there are examples of macroscopic phenomena that are inherently quantum, right? I'm thinking of superconductors or superfluids.
Yes.
However, you're looking for quantum effects in living organisms.
Yes.
My question is going back to Schrödinger's cat, if it's dead or alive. So what is, from a quantum physics point of view, what is to be alive or what is to be dead? Yeah. Like, what's your observable?
Yes.
Is that you? So maybe the answer is no. It's more in statistical physics rather than in quantum physics.
Yes, I think you're right. That's why I like to avoid this. You know, it's nice to use the Schrödinger cat as a motivation. But I think if you really want to analyze that physically, then you're asking exactly your question. What am I measuring? I want an observable with two outcomes. You know, the outcome 0 means it's dead and the outcome 1 means it's alive. And you would say, what property of this system would you actually measure physically to determine that? So that's why it's too complicated for a physicist. That's what I'm trying to say. That's why I'd rather talk about objects that we can still describe fully physically. And it may well be, ultimately, that in order to do that with an object like a cat, we'd have to control it under very low temperatures and so on, that it would no longer be living. I think Niels Bohr had a speculation like that. This guy applied complementarity and quantum physics to everything. And he has a beautiful set of lectures. I say beautiful even though I'm not a Copenhagen person, you know, so it doesn't matter. I don't agree with his philosophy, but I still love reading his stuff. And he made the point that maybe life itself is a fundamental property, just like quantum events. And you will have to take it on board as a given fact. If you really want to experimentally confirm that something is alive, you won't be able to do it. You'll have to kill it in order to experiment with it in a way to... And so he thought there was a certain complementarity between us being able to experiment physically on living systems and them being alive. And if this is true, then I think reductionism that I talked about really won't work. You know, we won't be able to do this kind of stuff maybe with living systems. I don't think that's the case, but it could be the case. I don't know how much time we have for questions. I'm kind of coordinating. I'm happy to stop as well if you... Okay.
Does entanglement come with a sense of strength or size? So in other words, the more massive the object, the less entanglement there is. And in the limit, does that reduce to classical?
It's a great question. Actually, that was my... I can answer this one. This was my PhD thesis in many ways, actually. And yes, it comes in different strengths. And you can quantify the strength. And depending on how much strength you have, you can actually show that you can perform different tasks, either in metrology. So if you want to estimate precisely a parameter, or more complicated computations or information processing like teleportation and so on. So if you want to teleport a single quantum bit, you have to have a maximum strength of your entanglement between two users. If you have anything less than maximum, you will never be able to teleport fully. So you can even quantify it in this way. What's weird, so of course the more massive the object, the more degrees of freedom it has to entangle to another one. So you're absolutely right. In principle, it scales with the size of the object. But what many people find weird, especially those coming from relativity, general relativity, is that it's completely independent of the distance between the objects. So you shouldn't think of it as a force, because we know forces, of course, somehow decay with the distance. But entanglement could be as big as you can make it for objects that are very far apart from one another. And unless something else interferes with this entanglement, it will just stay like that. And that's what's weird in some sense. Yeah.
If the distance is irrelevant as far as the entanglement is concerned, even over vast light years of distance, doesn't that put a big question mark against our fundamental understanding of time?
Yeah, this is also a great question, actually. There are many... This is why I'm usually dissatisfied after every lecture, because somehow there's so many things to tell you about, and you know, you have to remember them and you have to have the time. Yes, there is a big issue there, and I think one of the experiments I would like to see done, so it's a very simple experiment, actually. So what people can do is they have atomic clocks now that are so precise that they can measure down to 10 to minus 21 seconds, or whatever is the record now. So this is a clock that would lose less than a second throughout the whole age of the universe. You started at the beginning, at the Big Bang, and it loses less than a second up to now. I find it amazing. Now, what you can do is you can watch YouTube movies. I actually met the guy and I saw this for real. So what he does is he lifts the optical table where the atom is by 0.5 meter, and you can see the last few digits changing. He can measure the effect of gravitation across 0.5 meter height on our time. That's for real. I mean, it's not direct test of general relativity. There's nothing quantum about it, unfortunately. So what I'd like to do is I'd like to superpose this clock across 0.5 meter, And what quantum mechanics says is that it will be ticking at one rate here. It will be showing you 1 o'clock here and 2 o'clock over here. What does that mean? So what time is it now? And then you will probably come to me and say, well, why don't you measure it and see what it is? But that means time is as random in a way. It's a direct consequence of quantum mechanics. And I think no one really understands what this means. Or you could take two physical clocks and entangle them, put them in two arms of an interferometer. And now you'd be having two different times because of the ticking of clocks at different rates. I think these are the next experiments. I would love to see the outcome to these experiments.
So can we speculate they're in two dimensions of the same universe?
They are somehow in two different times. Actually, you're very close to using the language that David Deutsch likes, who is a big supporter of many worlds interpretation, and also not accidentally the inventor of quantum computers, because I think the two pictures go hand in hand. And I think if you ask him, what does it feel to be in another universe? You know, what does it mean to have a copy of yourself in another universe? He would say it feels exactly like being at a different instant in time. Just wait 5 seconds, and that's your copy in another universe. And actually, the picture of the universe that quantum physics would give you, if it's really fully quantized, would be very much like that. Different instances in time entangled to different configurations of space. It would be great to test that. I think it's a great question. Yeah.
I'm just going to pause it here because we can actually carry on the conversation next door, but I sense that the questions are slowing down slightly. Before we thank Vlatko, I'd like just to draw your attention to a couple of other forthcoming events. We have a weekly seminar series on Thursdays. That's all about climate change this term and next term. Tomorrow we are fortunate to have Professor Jim Hall here, who runs the Environmental Change Institute. He's talking about global water risks and the climate adaptation challenge. And on the 12th of March, the following Thursday, we have Natalie Seddon, who directs the Biodiversity Institute, on biodiversity and climate change. And we're coming at this from every angle because we kick off next term with continuing that series on human rights in a warming world. So do keep an eye on the website. And a couple of other major events coming. Thomas Friedman, the Pulitzer Prize winning author, will be here on the 27th of April. He won the Pulitzer Prize for his book, The World is Flat. He will be talking about technological change and globalization in a talk called The World is Fast, and that's going to be at the Sheldonium. We anticipate a large audience, so do go on our website and register if you're interested. That's on the Monday the 27th of April. And another perspective on climate change, we have Connie Hedegaard, who coming on the 18th of May. Now, she was the host minister at the Climate Change COP in Copenhagen in 2009, and then in 2011 pushed forward the timetable that is now going to culminate at the end of this year in Paris. And she has now stepped down from being the EU Commissioner for Climate Change, and will be talking, giving us a personal perspective of what it's actually like in the middle of those negotiating rooms at the heart of the process. So that promises to be a very interesting talk on Monday the 18th of May. But there are many other events, so do keep an eye on our website. Now, I said I was just pausing the conversation because you're all invited to the room next door as you exit there on the right for drinks, and we can continue the conversation with Vlatko. So perhaps we just conclude in here with a last round of applause for an excellent and very informative talk.